Good morning, students. I, Professor Ali Mudega, welcome you to the Design Lab. And today we can see about critical speed of rotating shaft is the name of the experiment. And the aim of the experiment is to find the critical speed of the given shaft. So, what is the critical speed? The critical speed is a speed at which the shaft tends to rotate violently. That is, it moves from its rotating axis and tends to vibrate like a, and it forms a loop. Okay, just like a skipping rope, you can see where it forms a loop. The same kind of loop is formed while certain speed when the shaft is rotating. Okay, and that speed is called as a critical speed of the shaft. So why we need to consider that? Because if the shaft tends to continue in the same speed, vibrates violently and forming the loop, that deflection will slowly will increase, and that tends to fracture in the shaft, and that reduces the life of the shaft. So we need to avoid that violating of the shaft, that is nothing but a vibration in the shaft, and we have to make sure that the shaft should rotate in its own axis. It should not violate its rotating axis. So that is known as the critical speed of the shaft. Okay, to conduct this experiment, the following things are to be noted down. The diameter of the shaft we need to note down. What is the length of the shaft we need to note down, and what is the density of the shaft material we should know. And we are conducting this experiment in the fixed supported end condition, where at one end of the shaft it is fixed and other end it will be supported. And for that we are going to note down two speeds at mode 1, that is when it forms a single loop, and speed of the shaft when it is at two loops, that is we call it as a mode 2. Okay, and later we have a calculation part that will come after the conduction of the experiment. Okay, let's move to the conduction of experiment. So this is the experimental setup of the whirling of shaft. So here you can see this is the shaft for which you are finding the critical speed. Okay, and here you can see one end is supported and one end is fixed. Okay, one end is fixed and one end is supported. Okay, so we need to measure the diameter of the shaft. Okay, we can measure with the help of the vernier caliper what is the diameter of the shaft, and roughly we find that the diameter of the shaft is 4 mm. Okay, from the manufacturer also we get what is the diameter of the shaft they have supplied. If you don't know, then we can, with the help of vernier caliper also, we can find the diameter of the shaft. Right now it is 4 mm diameter, and we need to find the length of the shaft. Length of the shaft from one end to other end of the shaft. From this end to this end of the shaft we need to measure, and that can be measured with the help of the this this scale. Okay, that can be measured by passing through like this. Okay, like this we can measure, and it is near about 765 mm. It is near about 765 mm. And this particular thing is provided to avoid the accident. In case of while rotating of the shaft, if shaft get slipped from these grips, it will come out suddenly, so that should not come in contact with the person who is standing nearby. Therefore this is cover which protect us from any kind of accident. Okay, and this is the motor which is connected to the shaft. This motor is going to run the shaft at the required speed. Okay, and that speed can be controlled with this speed controller. Okay, and here you can see initially the motor speed is 0 rpm, and as we increase the Okay, now you can see the speed of the motor is increased. To measure this speed, we have a sensor over here which is kept. Okay, here you can see the sensor is there. Okay, through this sensor it measures what is the speed at what speed the shaft is rotating. Now you can see the shaft is rotating its own axis, there is no loop, and as we increase the speed of the shaft, it forms a loop. Okay, now you can see there is a elliptic formation of the loop. Okay, observe it clearly, there is a formation of loop in the shaft. Okay, so this is the formation of the loop, and here it is only one loop is formed, so we take it as a here you can see the loop is formed from this end to this end of the shaft. Okay, there is a formation of a loop, so it is called as a single loop. At this loop, what is the speed that we have to note down? So the speed is near about 138 rpm. Okay, 138 rpm. So at this speed it is forming the single loop. So this is theoretical. Next we have to check with the this is the experimental speed. Next we have to check with the theoretical speed. Pause it.
चलो बोले
Pause it.
चलो बोले
Now the speed of the shaft is further increased to form the second loop, and here you can see this, the first loop ends over here, and from this length to the first loop ends over here, where you can see the deflection, and the second loop starts from here and it's ending over here. Okay, so this is the formation of the second loop. This is the formation of the second loop. And what is the speed that we have to note down? The speed is about 2650 rpm. Okay, these are the experimental rpm. Now we will check with the theoretical speed. Okay. After conducting the experiment, okay, for mode 1, that is small n is equal to 1 we write. For mode 2, small n is equal to 2 we write. Okay. For fixed supported condition, the experimental speed is 1370 rpm for mode 1, and for mode 2, 2450 rpm. And next we come to the calculation part. For finding nth frequency, it is given as omega n is equal to k square root of ei divided by rho into a. So to find the value of k, we write it as k1, since we are doing it for mode 1. For mode 1, small n value is 1, okay, and for mode 2, small n value is 2, that you have to remember. The formula for finding the value of k is 5 by 4 n pi by l. Okay, so 5 by 4 for mode 1, small n value is 1, for mode 2, small n value is 2. Okay, we are calculating for mode 1. So small n value is 1 into pi divided by length of the shaft, that is 765 into 10 raised to minus 3 meter. Okay. If I forgot to tell you this diameter of the shaft is 4 mm, that we have to convert into meter, 4 into 10 raised to minus 3 meter. Length of the shaft 765 mm, that we have converted into in terms of meter, that is into 10 raised to minus 3, and density of the shaft material is 7800 kg per meter cube. Okay. So after finding the value of K, now we need to find the value of I, moment of inertia. So pi by 64 d raised to 4 for a circular shaft. So after substituting the diameter value in terms of meter, we get I value as 1.256 into 10 raised to minus 11 meter raised to 4. Area pi by 4 d square, and after substituting the values we get 1.6 into 10 raised to minus 5 meter square. Later we need to find the F1, which is given by k square divided by 2 pi root of EI divided by rho A. Okay, and here the Young's modulus of the material we need to note down. The Young's modulus of the material is 2 into 10 raised to 11 Newton per meter square it is. So it is substituted as 2 into 10 raised to 11 for E value. K value we have already calculated, 5.133 divided by 2 pi, and E value is 2 into 10 raised to 11. I value here it is calculated, same value we have taken. This is the density of the material and this is the area of the cross section area of the shaft that we have calculated already. The same value is considered and we got F1 value is 18.54. So taking that value, we will find the critical speed of the shaft by multiplying with the 60. So 18.54 into 60 will give us 1112.08 revolution per minute. So that is the critical speed of the shaft theoretically. The same result is tabulated over here. For fixed supported condition, critical speed in mode 1 and mode 2, theoretical and experimental. For mode 1 theoretical, what we have calculated is 1112.08 rpm and experimental is 1370 rpm. And for mode 2, the experimental is 2450. What is theoretical speed? That you have to calculate using the above procedure. Okay, so please do the procedure and find this value. Okay, experimental. And the thing to be remember while finding the value of K, the small n value will be 2 for the mode 2. Okay, that is the only change. And remaining procedure will remain same. So calculate the value and we can complete the result table. So this will be the completion of critical speed of the rotating shaft, where we compared what is the critical speed of the shaft theoretically and experimentally. So this is the end of the experiment. Thank you. While doing the calculation, you need to remember one more thing. Okay, here you can consider the frequency Fn. We have taken as k square by 2 pi root of ai by rho a. So how it is taken? So this is how Fn is omega n by 2 pi. So what is omega n? Here we have k square root of ei by rho a. So if you divide this by 2 pi, you will get this Fn. So same thing we have done here. Okay, so this is the thing to be remembered. So this completes the calculation part. Thank you.